Hi everybody, Dr. Pingle here. I wanted to do a complete walkthrough of this notebook. There are a few people in class that maybe haven't taken Python before and a few that haven't used Jupyter notebooks before. So I thought it might be beneficial to kind of walk through exactly how this is done. So the idea here, in a previous video, I sort of showed you how to download and load one of these in. So this is a notebook that we're going to be using for the first one. And I've got some text here, so you can kind of read through this stuff. Everything that you see in a Jupyter notebook is actually editable. So if I click into here, you can start to see that this is actually a group of text. This is its own group of text, and so on. And the way the Jupyter Notebook works is there's a couple of basic categories here. You're either going to be declaring that what you're working with here is Markdown, which is a kind of a way just to say that it's text, or it's going to be code. So this is an example of code. And so you can change things around by changing them up here from code to Markdown. And you can see that the notation here, or the visual appearance of code, is a little bit different. It's got a colon here. If you run it, it'll have a line number and it says in and out. Whereas if it's just Markdown, then it appears like this. Now, Markdown actually, the Markdown part of it means that you can actually control how the text appears. So you can see how you've got different size of text here. So this is much larger and this is smaller. You've got boldface text down below. We even have things like links. And the Markdown is actually just HTML, or at least a version of it. So this is a Markdown that's not HTML, but it's just the pound symbol or the hashtag, and it just indicates that this is a heading. So if I hit Shift Enter, which is a way to run a cell and move to the next cell, it renders that as a header. And then the more hashtags you have, the farther down it is. So that's a level 1 header, that's a level 2 header, and you can kind of see the text get smaller, and it would look like this. So this might be like what you would use for a subsection or something. Okay, so we've got some text here. I'll let you kind of read through that on your own. Feel free to pause the video and kind of catch yourself up here. I'm kind of walking through what some of this means as we go. If we click into this cell, we can actually see some additional markdown. So this is B. So this is HTML, or it's borrowed from HTML. And anything between the B and its closing tag, the /B, is going to be bold. So in HTML, it's very important that if you're going to have an opening tag like this, then you have a closing tag, which kind of bounds the end of whatever it is that you're doing. So everything between these two is bold. And again, we'll hit Shift Enter to run that, or in other words, apply that markdown. We've got a bit here. As you're kind of working through this, you'll notice that these go in colors. So blue means that you're in command mode. If I click into this, you'll notice that it's green, which means it's in edit mode. And the difference between the two is basically, do I want to apply something? Do I want to write code, or do I want to write markup? Or am I trying to sort of make something happen about this code block? And there's a bunch of different things that you can do. You can look at these keyboard shortcuts for just kind of ideas. Many of these are on the GUI, the graphical user interface, above here. So, for instance, if we wanted to put a code block above this, we could say insert cell above, and it would do that. We can also use the hotkeys. So the D key is to delete, and you actually have to hit it twice for kind of like safety's sake, so you don't accidentally delete a bunch of your code. If I hit D twice and I'm here, that disappears. Okay, so let's talk about the code. So this is some simple Python code. I'm not really going to teach Python here, but it should look similar-ish to other languages that you might know, or you might just kind of be able to reason it out. This is a variable, and we're assigning the value of 5 to x, and we're printing that out. So just some very simple code. And you can run these code blocks by using the graphical user interface. So in this case, it prints the value of x, which is 5. But it's really going to be a lot faster if you use hotkeys. So I'm going to hit Shift Enter to run this block of code, and you can see that it applies A is set equal to 2, B is set equal to 9, C is set equal to the sum of A and B, and it prints that out, and so there you see an 11. This is a for loop. A for loop is a control structure that lets you move through usually a series of numbers. Range 10 means create a bunch of numbers between 0 and 9. And then you're going to print out the square. So some languages would use something like the caret or kind of the hat symbol. Python uses this double asterisk to indicate to the power of. So this is I to the power of 2. So as you move through this, I is set equal to 0 at first. So I to the power of 2 is 0. When I comes through again, now it's set to 1. Then it'll be set to 2, and it'll be set to 3, and so on. But every time, instead of printing out those 0, 1, 2, 3, and so on, we're going to print out the square. So it's going to print out 0, 1, 4, 9, and so on. So if we run this block of code, you'll see all of those perfect squares printed below. Now, all of these play-alongs are going to ask you to write code. If you haven't done Python, then you're definitely going to want to talk to B or talk to the TA, and we'll help you with that. And there are some examples online, or you can kind of mimic the things that you see up here, and that would be totally fine. But let us know if you need help. I want to, when you see these play-alongs, you're going to need to write 8 code blocks. So I could, for instance, insert a cell below, and I could write some things. C equals 9, print C minus 2. I'll hit Shift Enter, and I get 7. But again, it's often faster to use these hotkeys. So if I want to insert below, the hotkey for this is B. And again, you can find that out by going up to Help and Keyboard Shortcuts. And so you can see right here, A will insert a cell below, B will insert A will insert a cell above, B will insert a cell below, and so on. Okay, so you would write those 8 code blocks, and then that's what I would grade you on when you turn this in. So as you move through these, a lot of these are pretty simple. Numpy, we're importing these statements. If you haven't seen these before, these are bringing in packages or modules or sort of external pieces of Python that somebody else has written. And we can use those as tools, so we're not kind of reinventing the wheel all the time. If somebody has invented something that we can use, we don't want to write it ourselves. We want to import it and then use that. So we can print this out, and we have our second play along. So what is this one doing? This is saying, this is using the Numpy package. So Numpy's particularly good at using and manipulating arrays or groups of numbers. Sometimes they can be one-dimensional, which is what you see here. This is just sort of a list. Sometimes they can be two-dimensional, and we'll see that here in a second. So here we're creating some variables, or a single variable A, and we are setting it to be equal to this, what's called a list of numbers, 1, 6, 9, and 10. List is kind of means almost exactly what it does in English. But we're turning that into a Numpy array, which is just sort of a collection of things of the same type. Technically, lists can be of various types. So they could be words, they could be numbers, they could be a lot of things. In Numpy, though, it's important that they're all the same thing. Okay, so we print what is A plus B. And the way Numpy works, when you write an expression like this, it takes the first element of A and the first element of B, and it adds those things together, and you'll see 6. The second element of A and the second element of B, so 6 plus 2, and you get 8. So you can kind of see the pattern here. So this is sort of a piecewise or element-wise addition. We take the first one and we add it to the first one. We take the second one and add it to the second one, and so on. We take 1, we subtract 5 from it, and we get 4 for the second line, print A minus B. Print A times B does the same thing, so 1 times 5 is 5, 6 times 2 is 12, 9 times 4 is 36, and so on. A to the power of 3 means 1 to the power of 3 is 1, 6 to the power of 3 is 216, and so on. So you kind of get the idea. This kind of applies these what's called element-wise, or each little piece or each little number at a time has something happen to it. So here we have another play along. We can hit escape to enter the edit or to enter the command mode. We can hit B to create a cell block below that, or we could have just gone insert and insert cell below. But the hotkeys really do make life easier. So this says create 5 different arrays, at least 3 of the same length, and perform some kind of basic calculation on them. So we could say A is equal to np.array. And you can have negative numbers and you can have very large numbers. So there's our first one. There's our second one of the same length. Here's a short one. Here's a longer one. And I guess this one should be also 5 long because we want 3 of the same length. So 1, 2, 3, 4, 5. All right, so A, B, and C are all of the same length. All of those have 5 pieces to it. And it says perform some kind of basic calculation on them. So we could say print A squared, print B plus E, and so on. Okay, so you can kind of do a couple of these. What about something else? How could we? So we can try this out, and that all works fine. I'm going to create a new code block below this. What would happen if I said print A plus C? Here we have an element of 1, 2, 3, or we have a list of 1, 2, 3, 4, 5 elements. C has 2 elements. How is it going to match these up? And the answer is it's not. It's really important that if you're going to do this kind of manipulation, that things match up. I can't add, or Python doesn't know how to add 5 numbers to 2 numbers. It just doesn't work very well. Generating random numbers is kind of one of the fundamental ways in which we're going to run a simulation. So kind of moving from just sort of scripts of Python to something maybe a little bit more useful for spatial analysis. One of the techniques that we're going to use is Monte Carlo, which is a way of kind of adding randomness or repeated tests to a simulation to try to get a sense of how variable the results might be. And this is all based on random numbers, and so this next section here kind of talks a little bit about random numbers and how they work and how you can generate them. So this first example says x equals np, so that's numpy, dot random, which is kind of a little sub-package, and then dot rand, which is a function. And we're going to pass it the number 1, which means I would like you to make 1 random number for me. So if we run this block of code, we get a random number. Now, this says hitting Control-Enter instead of Shift-Enter will keep you focused on the same code block instead of advancing. So sometimes, as you're moving through the code, we kind of want to be able to step through and kind of run this block and then run the next block, and so it's faster to just hit Shift-Enter to move through your code. But sometimes you want to keep running your same code over and over again, which is what you're asked to do here. So if I hold down the Control key and hit Enter, I stay in the same code block, and I just keep generating random numbers every time. And you'll notice that the numbers are pretty confined, so they really only go between 0 and 1. And you could probably hit this a million times, and you'll never see the same number twice. It would be next to impossible for that to happen. What happens if you change the number from 1 to something else? So in this case, it's always nice to have a separate code block for each piece here. So we're going to create a code block below. We're going to paste what we saw above. And we're going to say, what happens if I put a 10 in there? Well, what happens is I get 10 different numbers. And you can start to get a sense and compare what's going on between these. So you can see, for instance, that again, we're never getting any values that are less than 0, and we're never getting any values that are greater than 1. We can generate 2 arrays of length 10. So we could say A equals NP random dot rand 10. We could say B equals NP random dot rand 10. And we could print their sum like so. And you could print the difference in the product in pretty much the same way. There's some demonstrations here. Here we're making 100 random variables, and we're saying print whether x is less than 0.5. So for each of those 100 random variables, it tests and it says, was this first one less than 0.5? No. Was the second one less than 0.5? No. Was the third one less than 0.5? Yes. And so on, all the way through. And if you want to get a look at how this turned out, you can do something like this. You could say print x, and there we can kind of match up both the original array that we generated plus the result of each of these tests. So was this first one less than 0.5? Nope, it was greater. It was 0.51, and so that one's false. Was the second one less than 0.5? Yep, that one was 0.01 and change, so that one is true. It is less than 0.5. And you could match up all of these to the ones that you see here. This code block is just asking you to, we've got a little bit of code here, so we're saying we're generating 100 random numbers, and then we're printing those out. So this first one says, print me the sum of all of the values that were greater than 0.5. So for each of these 100 numbers, we do a test like you saw above, and then we add up how many trues we found. Right? So we could do something like that. And these are just 2 ways of writing the same thing. Some simple math is encoded in very basic core Python, and some more advanced functions you're going to have to use things like Numpy to do. So if it's really simple math, there's probably a command like sum that you can use. If it's anything more than just the basics, you're probably going to want to use Numpy. So no matter how many times I run this, those numbers are always going to be the same because they're both calculating the sum of wherever the x's are greater than 0.5. And you can see that they are hovering around, but not always equal to 50, right? If I generate, sort of like flipping a coin, if I generate 100 random numbers, what's the probability that it's going to be above 0.5? Well, it's got basically a 50% chance of being above 0.5, and so that is essentially a coin flip. So what you should find is that these hover around 50, but aren't exactly. If I flip a coin 10 times, I might get 5 heads, but I might get 6 heads. That wouldn't be so unusual. So this can kind of help you get a sense of how random can be. And you can run this as many times as you want and see what your highest or your lowest number is. 54, 55, 62, right? So some of those high numbers are not so unusual, but you're probably not going to see 99 no matter how many times you do this. Okay. Number 5, play along. How many times did you run the code? Did the results conform to your expectations? Why or why not? So here you would just, instead of writing code, you could add a code block here, and you could write up an answer, and you just want to make sure you change it to Markdown so that it looks very nice. Okay. This next section here, we're creating 10,000 random numbers. We're creating a histogram of them. Why would we create a histogram? Because we don't want to print 10,000 numbers to the screen. So instead, we start inspecting our distributions that way. And here we have to use a different handle here called PLT, which is what we brought in our graphing function as up here, kind of at the top here. So we brought in matplotlib.pyplot as PLT. So that's what we're using for graphing PLT. So plt.hist for histogram, x, and bins equals 50. So we should have 50 little bars here. You can see that we're counting how many were in this little section between 0 and call it, 0.0. Well, we could calculate that out, but 0.02 is about right, and so on. We had 200, and here we had, call it 175, and a little more than 200, and so on. So this is sort of a random number distribution. We've got a little bit of variability here, like we would expect, right? If you flip a coin 10 times, you might get 5 heads, but you might get 6 heads. So it's not totally even, but it's pretty close. For part 6 here, you can sort of answer these questions, and we're moving into the next bit here where we're talking about two-dimensional and greater dimension random number collection. So in this case, we're making one vector of random numbers, which is just to say a one-dimensional array of numbers, a sequence, a list. We're creating another one, and then we're plotting those together as if they're sort of x and y coordinates. And if it helps you to think of it that way, you could just call them x and y instead of a and b, and it's the same thing. And it's nice to kind of run this a few times and get a sense of how random things are. And this is essentially as if we've sort of got a bunch of dots in our hands and we shake them up and we let them go, and they kind of fall on the page however they want, and they just fall randomly. We can create a two-dimensional array of numbers, which is to say like a matrix or a raster would be another way to think of this. Images are essentially two-dimensional collections of data. And here we're creating a bunch of random data 5 by 5, and it looks like this. So we have 5 rows worth of numbers and 5 columns worth of numbers, all of them between 0 and 1. We can visualize this. We could print them out, but obviously once they get pretty big, we don't want to print out this many numbers to the screen. So just like we did before with this one, we're going to try to visualize this with a graphic. So we run this little block of code. We get something that looks like this. I don't know how many of you still have seen any analog television sets, maybe in the movies. But when you used to turn an analog TV to just no station, where no station was broadcasting, you get this kind of snow effect, these random moving dots on your screen, kind of like static. And that's what we've got here. So here what we're doing is we're coding the lightness or darkness based on the random number. And if we want to kind of visualize this, we can do that by making these numbers a little bit smaller and maybe printing out their value. All right, so here we have random numbers that we've generated, 3 by 3, 3 rows, 3 columns. This one is 0.18, this one is 0.13, this one is 0.83, and so on, and we're visualizing these. Now these are a little bit off kilter. You may notice that these don't quite match up. In this case, this is actually inverted. So your 0.18, instead of being this value, is actually this one. 0.13 is this one. 0.83 is this one. 0.85, 0.79, 0.52, 0.24, 0.54, 0.33. So it's a little counterintuitive, but the idea here is the larger the number, the darker the value. Sorry, got that backwards. The smaller the number, the darker the value. Now, what's controlling how that looks is this word. So gray is what's going to apply a color map. So that's why it's called CMap to this matrix. But we can change these around. So the play along says the appearance of the above plot can be configured with the CMap parameter. If we click on this documentation, we can actually get a good sense of all of the different things that we could make. So some of these look pretty cool. Magma looks pretty nice. So if we just copied this piece here. And instead of running this gray, we could run it magma. We would get something that looks like that. And there are a lot of examples here. You can kind of play around with these if you want. You can reverse things. Some of these have reverse color maps by appending a underscore R at the end. So let's see if we can make an example here. Gray and gray R. All right, so that's going to reverse it. So in this case, the darker, the bigger the number, the darker the plot, but it's still flipped upside down. So this is 0.24, 0.22, 0.36, and so on. Okay, let's see. So random numbers can actually be generated in a couple of different ways. Actually, more than a couple, probably dozens at least, if not hundreds. And the random number generators that we're using up here are what are called uniform random number generators, which means that they're just as likely to be above 0.5 as below. They're just as likely to be between 0.75 and 1 as they are between 0.5 and 0.75. All right, so the histogram that we see here indicates that any number is equally likely to be generated. But there's another kind of random number generator called a normal random number generator, and that's here, or at least here's one example of it. And the n at the end means normal. If we run this, we've generated a random number of negative 0.4, 0.3, 1.5. So these have a very different character. First of all, they can be negative, the ones above. The uniform random generator never produces a negative number. But they also are not bounded by -1 and 1. If we keep running this, we'll eventually hit something that's much bigger. So this is negative 1.90. And in fact, this is what's known as a continuous distribution, which means theoretically any number is possible. Although in practice, you'll probably rarely see numbers that are beyond, say, positive and -3. And this code block asks you to run this 20 times and tell me what your largest and smallest numbers were. So smallest one is -1.9 so far. There's a -1.6. There's a 1.6, 1.89. So you'll just kind of keep track of these as you go. And if you want to make life easier on yourselves, you could maybe do that, right, and generate 20 of them. Look for the biggest and smallest that way. That would be fine. Okay, so otherwise you can generate the same number of things. We can inspect these things with a histogram. You'll notice that this histogram looks quite a bit different, right? It's much more likely to generate something close to the mean value of 0 than it is to generate something over here. And compare that with the histogram that we saw above, where it's equally likely, a little random variation aside, but it's mostly equally likely to generate any of these numbers in this range. We can do the same thing as we did before. We can generate scatter plots with these. You'll notice that these tend to be a little bit more circular, right? Because we're sort of generating values that are going to be close to the mean, kind of between 1 and -1, or, you know, most of our circle is going to kind of be in here instead of, you know, these corners are kind of empty. And they'll always be kind of empty, right? A little randomness aside. And we can generate random numbers that look like this. And generally what you'll find is that these tend to be, again, clustering a little bit more around the 0. So these will look a little less variable than these up here. Right, so in comparison, we've got a lot of whites and a lot of blacks. Here, what we see is mostly grays. Right? Okay. We can do things like run correlations on these things. We're not going to get too far into the details here. But here we're just using a standard Pearson correlation that goes between 1, which means perfectly correlated, and -1, which is perfectly uncorrelated, um, sorry, perfectly negatively correlated, and then 0 is no correlation at all. So that means we essentially can't, even if we squint, we can't really see a line here, and we can kind of run that multiple times, um, and you can start to see what kind of a correlation you'll get. If you run this a lot, you'll eventually get some correlations that are pretty high. So far nothing too big. 0.39, that's almost there. This code block is asking you to try to find one that's above 0.5. There's a 0.41 that we saw go by. It'll go, believe me. 0.47. Oh, there was 0.57. All right, good enough. So if you go past it, don't worry. I'll believe you. But how many tries did that take? I don't know. Maybe we probably should have counted, but maybe 30 or so. Okay, modeling mortgage failure. So this is the last section, and this corresponds with Chapter 1 of Nate Silver's book. And the idea here is that we wanted to model how mortgage bundles failed. The idea behind mortgage bundling or collateralized debt obligations, or CDOs, is that we want to allow people to bet on the likelihood that a lot of mortgages are going to fail. The financial reason for this is that it sort of provides funding for an insurance model. But effectively, as an investor, you don't really care about what it's being used for. But I want to be able to give you, a big chunk of money, $100,000, and then, as long as nothing terrible happens, as long as not all of the mortgages fail, then you give me, $10,000 back plus my winnings, right? Which is a small percentage, but that's how these things work. And effectively, I've lent you money and you've paid me back with interest. Now, the idea behind these bundles of mortgages is that they were rated as being having a certain degree of safety, and the idea here is that if all of the defaults are perfectly correlated, then this should only fail 0.00003% of the time. Now the problem is that it could be the case that if one mortgage fails, then the next one is more likely. And the extreme case is that if any one fails, then they all fail. And if that's the case, and we're sort of assuming that we've got each mortgage has a 5% chance of failing, then effectively what we've got here is if one goes, they all go, which means that if any of them hits, then we lose this whole bet, right? If one goes, they all go. And so what should have been a very safe bet is now actually a fairly risky bet. And in fact, it's 160,000 times riskier than we thought. So if you told me that this is a safe bet, it actually turns out to be quite a risky bet, and more people will lose money than we expect. And so Silver argues that this is how part of the mortgage crisis kind of exploded into a much larger financial crisis. Now, the question that I wanted to ask and maybe approach with a random number simulator is, how could we calculate these numbers? And the answer is we could just simulate each mortgage with a random number generator, pull out a number between 0 and 1, and if that number is within a certain margin, and here we're saying 5% is our risk of failure, so if it's within 5%, then we assume that that mortgage has failed, and we model that as a defaulted mortgage. Now, how can we do that? Well, we could generate a bunch of random numbers. In this case, 5, right? Because we're playing around with this
pool of 5. We print out the values of those. So here, that first one hit 0.95, 0.93, 0.47, 0.47, 0.8. All of these are above 0.5, so none of these failed. And if we run these, eventually we can find one that does fail. So here we see one that hit 0.02. That's under our threshold of 5%, which would be 0.05. And so this particular mortgage failed. But did they all fail? No, they didn't. And in fact, that would be pretty likely. You could run this code block all day long, and you would almost certainly never find a case where they all failed. The odds of that are very low. The odds of that happening are 0.00003%. So the question here is, how are we gonna model this for much larger values, right? We don't really want to just hit Control Enter, Control Enter, Control Enter. What we want to do is simulate this a very large number of times. So we could write this out this way. This is a simple for loop, and we have k equals 5 times 10 to the 6, which is 5 million. And so that's how many times we're going to run this this simulation. So for I in range k, so for I in 5 million, generate 5 random mortgages. Find out how many were under 0.05, find out if that happened to all of them, and then if that's true, tell me where that happened, right? So essentially we've got 5 million pools of 5 house pools, and we're going to find out if any of them all fail. So we run this code, and it's going to take a while. So this is our first block of code that maybe has run for a while. You can see there's an asterisk right here. That means this code block is running. And we found iteration 622,375 had a case where they all failed. We hit another one at about 1 million where they all failed. Remember, we're running this 5 million times. There's another one. Nearing the end. Okay, here we go. So out of 5 million trials, only 3 had a case where they all failed, right? So that's a probability of about 3 in 5 million. And you could time how long that took. You can ballpark it. That's fine. Maybe this took, call it 15 seconds. Most of you will find a failure. Some of you will find more than one. A couple of you will probably have none of them fail, which is totally fine. All right, but the way we wrote this is actually not very good Python. It took a while. It may not seem like it took that long to run 5 million trials, but in computing time, it was actually quite inefficient. And so there are better ways of doing this, and I've got a couple of examples here. This is an example of setting up a pool of 20 iterations. We're generating, instead of generating our random numbers 5 at a time, we're generating our random numbers 20 by 5 at a time. In other words, we're generating our whole random pool all at once. So if we hit this code block, we're testing 20 pools to see if any of them had all of their mortgages fail. So that would be as if we stuck the number 20 in here. All right. Now running this 20 times, that doesn't take very long. You could run this all day, and you're probably still not going to come across anything. But let's try running this 5 million times. Okay. So what did we just do? We just did exactly what we did up here. We're generating 5 million trials of 5 mortgages each, and we're testing them all out at the same time. Now, you don't have to understand this code. If you want to dig into that a little bit, I think you might find it interesting. We're testing whether all of them failed by row, and then we're finding out whether any of the rows had all of them fail, and in this case we didn't. So again, we tested this 5 million times, exactly what we did up here. This code block took 15 seconds. This code block took less than a second. And we're hitting failures. We're not reporting exactly the same information, although we could, but we're saying we had a failure, we had a failure, we had a failure, we had a failure. All right. We're really more interested in comparing how this worked in comparison to Nate Silver's table above, right? So this is table 1, 2 out of his book, and he gives us some odds here. The odds of them all failing are 0.00003. The odds of one of them failing are about 20.4%. So how could we do that? How could we calculate those? Well, we could do it with math, but we could also just do this by simulation. So here we're generating 10 million runs. The higher the number, the more reliable our estimates are going to be. We're going to tabulate how many of them failed. We're going to print out how many in 10 million had all 5 fail, and so on. So we're going to try to regenerate the table above with just a simple random number generator. 10 million trials all at the same time. In this particular case, we had 6 in 10 million had all 5 fail. 0.003 had 4 failures. 0.1 had 3 failures. 2.3 had 2 failures, and 22.6 had 1 failure. And if you compare those numbers to what you see above, they're pretty close. And they won't be precise because we're simulating, we're using random numbers. Again, the bigger this number, the more precise they're likely to be. If we run this again, we're likely to get a slightly different result. But you know, within reason, these numbers should square pretty nicely to what you see up here. So why would we do that? We wouldn't necessarily do it in the case where the math is easy to figure out. We do it in a case where the math is much more difficult to figure out, where the rules of the game are a little bit more complicated. Some games are pretty easy to calculate odds, so if you're playing Texas Hold'em, it's fairly easy to calculate those odds. But if you're playing a more elaborate game, it can be quite a bit harder. And so that's one of the reasons why this kind of numerical simulation, this Monte Carlo simulation came around, was to enable us to test ideas that are maybe a little bit too complicated to express in just mathematics alone. Okay, well that's your walkthrough. That's a pretty quick trip through this stuff. If this stuff is new to you, you should definitely talk to me. You should talk to the TA, and we can help you work through these issues. Give yourself plenty of time to work on this notebook. You're definitely going to need it, and hopefully the text kind of helps help you work through a lot of these little code blocks. All right, thanks very much for listening, and we'll catch you next time.